Now we're ready to build our differential equation for blood flow. When we speak in terms of the flow, I'd like to point out that the flow represents change in arterial volume, in other words, looking at the change of how the volume changes of your artery. And the flow represents the change in this volume. And this is modeled as the difference between the rate of flow entering the aorta which remember is going to be pumped to the rest of the body, and the rate of flow from it. So we're looking at the difference between the incoming and the outgoing with regard to the aorta. Okay. We also know that we also take note that the aortic valve is closed during the systole phase. So that means that there's no blood entering. That's going to be useful. That's actually going to help us with the particular initial condition. All right? So here's what we know. The rate of change with respect to time of your arterial volume is the difference between the flow rates, the flow of the blood, flow rate in the aorta, minus the flow rate out. This last term, we've already defined it. It's going to be the volume, cardiac volume, QS, during the systole phase. But we just said the aortic valve was closed and there's no blood in, so we'll model that as 0. So the differential equation is fairly simple. d sub a t with respect to time t is just 0 minus q sub s of t. And then going back to, again, our definition of blood volume during the systole phase, this is negative 1 over Rs, remember our resistance, times the pressure, arterial pressure. Right? Now, again, playing off another particular relationship we know, but recall that arterial volume also is the product of the compliance times the pressure. So, if you take that piece of information with what we've got thus far, combine the two, what we know is then that the rate of change, actually simple that, we know that the rate of change of the arterial volume as a function of time is Ca times the derivative of that arterial pressure, just taking the derivative of this very simple equation because that's a constant C sub A. This we know is also supposed to be minus 1 over sub R sub S, PA of T. So combining that two pieces of information, we can totally eliminate arterial volume. And what we have then is this right here, which suggests that the rate of change of arterial volume with respect to time t is minus 1 over the compliance times the resistance. And that's multiplied by PA of T, with the initial condition that the initial pressure is, by definition, that value of the systolic pressure of the heart. One way of looking at this particular value here, PYS, this is your max pressure to close the aortic valve. So that's what's necessary to keep that valve closed. All right? So you have your differential equation now. Here it is. Here's the IVP that defines the rate of change of the arterial volume. Pressure of the rate of change of the arterial pressure. Right? Solve this linear differential equation. Solution. Difficult to see. That initial condition, it'll be the maximum pressure to close the aortic valve, that systolic pressure constant, times E to the minus quantity T over that product, CARS. Okay? And this will be the solution as time marches from 0 on to the final beat duration, time T. So in our next video, we're actually going to use this particular solution to help do a prediction of some very important physiological quantities that are useful to help compare the performance and the health of people in general.